Hello everyone and welcome back. So this time we're going to be talking about the instantaneous center of zero velocity. What is this? It's magic. Okay, seriously magic. Like the last section, not fun. This one, fun. So what you're going to do is learn how to find this magical instantaneous center of zero velocity and use it to determine the velocity of any point on a rigid body in general plane motion. It's magic. So let's jump right into it. First off, why do you want this? Well, the instantaneous center of zero velocity is a point on your object or outside of your object that would have zero velocity. Like if your object was suddenly to get bigger and include that point would have zero velocity. For a bicycle, when we're thinking about it, for the general plane motion of the bicycle wheel, this point right here at the bottom, that is the instantaneous center of zero velocity. Because with respect to the ground, it doesn't move. And using that, we can find the velocity of any point on that wheel. They might be thinking, well, the velocity of every single point is just tangent, right? Well, you're correct that they all have a component that is tangent. However, the bicycle itself is moving forward, so when it comes to the ground, the rotational velocity plus the translation velocity, it's going to equal 0 here, and it's going to get bigger as we get towards the top. So which point on the wheel has the maximum velocity? Well, it's the point that's farthest away from this instantaneous center. And does a larger wheel mean the bike will go faster for the same amount of effort in pedaling the smaller wheel? That's something you have to think about. I'm not going to tell you. Okay, how about right here? So as this board slides down the wall to the left, it's subjected to general plane motion. That's both translation and rotation. Now, we know how to solve this. We know the directions of the velocities. If we know just a little bit more information, like maybe an angle and one of the velocities, we can solve for everything else. But where would this instantaneous center of zero velocity be? Because you can see that this ladder right here is not going to be 0 anywhere. It's going to be moving the entire ladder. Well, the instantaneous center doesn't have to be on the object, okay? It can be off the object. It's just always only with respect to time, because it's instant, every instant in time, and for a particular object. And so if we want to figure out what the direction of the velocity of the center of gravity of the board is, well, our instantaneous center could actually help us figure that out. Okay, so for any body undergoing planar motion, there always exists a point in the plane of motion, not in the body necessarily, but in the plane of motion, in which the velocity is instantaneously 0. That means that it is 0 velocity there, and if its body isn't connected to that point, well, obviously that part of the body, there's no point there, but if the body was there, it would be 0. But remember, it may or may not lie on the body, and many times in many problems, it's not going to be on the body. So if you can find this point, if you can figure out where it is, then you can determine the velocity at any particular point you care about. So let's look at some blob math. First off, we have a blob right here. This is the blob. And there's a whole lot going on here, but we know that this blob is rotating, okay? It's rotating, and it's going to be translating too. And we're trying to find out where this instantaneous center is. Well, if we know the velocity and we know its angular velocity, we can solve for where that instantaneous center is. Because for one, the position vector to the instantaneous center and my velocity vector are always perpendicular to each other. And second, we can calculate the length of that position vector using this equation. We can see how the velocity is connected to the angular velocity, and from that find the instantaneous center. Now, if we have two different velocities, perhaps we don't even know the angular velocity. Maybe we don't, maybe we do. What we can figure out, though, is that both of these are rotating around this instantaneous center of zero velocity. We know that they're both rotating around that. And so if we were to draw a line perpendicular to those velocity vectors, and we draw it all the way off to the edge, eventually those are going to intersect. And guess what? They intersect at our instantaneous center of zero velocity, and we can solve then for those velocities, or for the position vectors, or whatever else we need to know, because that ratio is going to be the same. So all of this is going to come down usually to triangles. You can see these kind of triangles here. These are similar triangles. They have the same slope, just different side lengths. Same slope but different side lengths. And so the ratio of any two particular sides is going to be the same for both of these. So if you have two velocities, one going right and one going left, then the instantaneous center is going to be somewhere in the middle of those. If you've got two velocities that are both going in the same direction, they're parallel, the instantaneous center is going to be somewhere outside of that body. Now, not between them, but above them or below them. And you can use these triangles right here to calculate it. If it's all drawn to scale, it actually becomes very, very simple. Just take a line, connect the endpoints of your velocities and drag it up. Connect the points that they start from and drag it up, and they'll intersect. Same thing right here. Connect their beginning points, connect their end points, and it will intersect right at the instantaneous center. It's one of those times when you have some graphing paper, you can really do some good math here and make it easier on yourself. So once you have found the instantaneous center, then you can figure out the velocity to any particular point you want. You'll use whatever your first velocity was to calculate your angular velocity around this point. And then you can choose any point you want, and you'll know, well, my velocity has to be perpendicular to that point. And if I know what the distance is, I can then calculate the velocity. And you're good to go. You start, and it's beautiful. It's so much simpler than we learned in the last section. So let's jump right into this and try it out. So next time we're going to try out an example using this to solve a problem that's very similar to what we saw last time. So thanks for listening. I hope this helps you, and I'll see you all later. Bye-bye.